speaker mode.
Okay, good afternoon, everybody. Last lecture, we just explained the definition of signals and the systems, right? So I'd like to ask somebody, what is signal in general? Somebody define the signal. Yeah, just somebody, just go ahead and loudly. Change of information or?
Transfer of information.
Yeah, you don't have to make transfer. It's a process when you transfer the information, but you can say it's a set of data information. And most of the signals that we're going to operate with this semester, it's like function of time or be function of time, because there are many kind of signals. That's what we're going to focus on. And systems. What are systems? Exactly. Processing the input signal to reduce output signal for something useful. What is signal processing? For example, here we have in communication system we explained previously. So we have signals and we have systems and we have signal processing. What is signal processing? The word itself, process, what does it mean? Some kind of operation will be done over the signal, right? So give me some operations. That would be the processing. In this system, for example.
Like changing from one type of signal to another.
Exactly. Changing from one type of signal to another. Like if you have analog signal, then we convert to digital signal. We're going to have today both types of signals. Another example, you have here electronic processor that the electronic signal here is going to this unit, and then it will convert it to current and voltage. Another thing, maybe the signal is really weak. We need to make it stronger. So we have amplifier. Amplifier can be processing. We have signal and noise imposed in the signal. And we want to make it clear so you can hear the music clear without the noise. So we have filter to get rid of the noise. That's processing also. So there are any operation performed on signal, we consider it signal processing. Okay. So I give here in some examples of signal processing: amplification, filtering, modulation, and demodulation. That's performed on analog signal. And digital signal, we have compression, error checking, error detection, and we're going to explain that in detail in the future once we go to the digital signal. And there are many applications, of course, for signal processing, like audio signal processing, image processing, video processing, wireless communication, as we explained last time, control system like temperature control system, and even in financial signal processing, also we deal with it. Because the data that you have in finance, it's data, it's signals, considered as signal. Okay, and changing with time. You go to stock market this year, next year, before, it just changed. So let's start with the classification of signals. We can classify signals to different categories. The first category you see here, the time. How can you classify the signals with time? So maybe the signal is continuous with time. What does it mean? Every single second, not every single second. Any instant you want to find the information of the signal, you will see it. Like what? Like if you have a signal like that, sinusoidal, maybe it's some electromagnetic wave or maybe voice, whatever signal. Let's say just it's ideally sinusoidal. So when you look at the signal, we say that's continuous time signal. Why? Because that's the independent variable time, and any time you want to find the value, you will see a value, the amplitude of the sine wave. For example, if you have at 0, you have value. At 1 second, you have between 0 and 1, you can find millions of values. So once you have value at any time you pick, that's a continuous time signal. The second type, discrete time signal. And discrete time signals, from the name itself, it means you have values of the signal at a specific instance, not at every time. Like you have maybe at 1 second, at 2 seconds, 3 seconds, but between 0 and 1, you don't have any information. The information at 0 here, it's equal 0. At 1, it's equal less than 0.5. And at 2, it's above 0.5. But between 1 and 2, you don't have anything here. So the discrete time signal is defined at discrete moment of time. And we use the abbreviation here, CT, it means continuous time signal, DT, discrete time signal. How you convert from continuous time signal to discrete time signal? We use something called sampler. Simply, sampler is a switch, on and off. When it's off, nothing will go. Like, let me. So the sampler, you can represent it as a box, and it has input. It's a continuous signal, and it has output, discrete. How do you make the discrete time signal? I'm going to sketch the same signal, the input. What do you do? They will have like a switch here. Of course, electronic switch, could be a circuit, simple circuit, complicated circuit. It's a switch, electronic switch, on and off at a specific instant. Let's say that it will turn on every 0.1 second. So every 0.1 second, you will find a sample, like that is 0. At 0.1, that's a value. At 0.2, it will just take this value here. At 0.3, it will have this value. At 0.4, have this value, and so on. So you continue, you got the discrete time signal by this sampler, and then you will not have this continuous. They will disappear if we just if we erase it. That's what we get. Or of course, we got to continue to complete the whole thing, but that's what we get. Just samples, samples at each instant, at every 0.1. Yes.
So it's basically just a switch.
It's a switch, sampler is a switch, simply. But it's a circuit, actually. But you can represent it as a switch. You can have transistor, MOSFET, anything, turned on, turned off. It just will slice the signal. And it will be at every 0.1. Not necessary to have TS sampling period equal 0.1 second. Could be 1 second, 0.2 second. We are going in the future explain how can you control this sampling time, or what are the restrictions on the sampling time. Because you are not free, just say, okay, I'm going to sample the signal every 0.1 second or 1 second. No, there are some restrictions. So we can restore the signal back. So when you look for the, let me make it bigger a little bit. So if you look at the part we slice it here, you have something here, another signal, sample, and so on. So this one at time 0, that one at 0.1, at 0.2, at 0.3. So this represents 0, it means 0. That's TS, sampling period, is equal 0.1. What's 0.2? It's 2 TS, right? 2 TS. And this one, 3 TS. And so on, you can continue 3 TS, 4 TS. So they said, okay, we may express discrete time signal as a sequence, because we should write it like that. This value, the value here, it's equal x of 0. The value at the second sampling, it's equal x of TS, right? And the value here is x 3 TS, x at 4 TS, and so on. Let me give a numerical example. Let's say that the sine wave, I know the sine wave, it's equal 100. That's a signal x of t, continuous time, right? X of t. 100 sine, let's say omega t, anything like and choose omega any value, just for simplicity. We'll say 10t. So if I want to find the value at 0, that's simple. I'll put t equals 0. So I'll say x of 0 equal 100 sine 10 times 0. So equal 100 sine 0, 0. All right, that's easy. What about the second sample? The second sample, I'll write x ts. And we know ts is equal 0.1. So all what I'm supposed to do, I substitute by t equal ts 0.1. So I say it's equal 100. I'm looking for this equation, okay? Sine 100 t. I replace now t by ts, which is 0.1 times. I'm sorry, this is not 100, it's a 10, right? 10t, and t is equal 0.1. So that will be 10 sine 1. And then I will go to the calculator and calculate the value. Yes.
Would it be 100 sine 1?
100 sine 1, yes. And then the sine 1 has a value, and you should substitute by radian, 1 radian. So if I do that, sine, let me first change the mode of the calculator to radian. Sine. That will be equal to 0.84. Sine 1 is equal 0.84. So it will be equal 10 times 0.84 will be equal to, oh, that's 100 here, will be equal to 84. So the value of x of ts is equal 84. So the value of this xts, I can just mark it 84. What about if I go to the second, I'm sorry, the third sum, it will be x 2ts. It will be x, and 1 ts is equal 0.1, so it will be 0.2. So I'll have 100 sine 10 times 0.2. That will be equal 100 times sine 10 times 0.2, 2. And then I evaluate, that's radian also. So I will evaluate it. I will say sine 2 and I got 0.9. So I will have 100 times 0.9 equal 90. And you continue. They want to express the discrete time signal as a sequence. How do they do that? They said instead of writing xts, x2ts, 3ts, so, and I know ts is constant, why I don't write like that? Instead of x0, I make it square bracket x0. It means when n equals 0, x1, x2, x3, and so on. What is 0, 1, 2, 3? Because every time I'm multiplying ts by an integer, 1 times 0, 1, 2, 3. What this number 0, 1, 2, 3, 4? That's the index, and we can call it n. So at time t, it's equal n time ts. ts is the sampling interval, and n integer 0, 1, 2, 3, 4, and so on. So that's the way they express discrete time signal. And then now we have it as a sequence, x0, x1, x2, x3. But I understand when you say x2 means add 2 ts, but you don't write ts, you write just x2 and you write the equivalent value. So that's how you convert from continuous to discrete. And here you see in this figure, that's the continuous time signal, and that's the equivalent discrete time signal. It's the same, but just you got sample. Why we do that? Because if you are going to have the signal input to a digital system like computer, microprocessor, and as you know, these days we're using a lot of digital devices, so you got to convert it. So you got to sample it. Of course, this signal, there are other things going to be done so the computer will accept it, because the computer only accepts zeros and ones. There is something called quantization. They take each sample and then make it like quantization, see what's equivalent to what number in zeros and one. It will be like series of zeros and one pulses to go to the computer. But we don't want to go through that. We're not explaining computer engineering. We're just saying that's the first step and how you convert it to discrete time signal. So through the semester, we're going to have operations on both continuous time signal and discrete time signal. It's not difficult, it's easy, but it's very important to know how we deal with it. If you add two signals, if you impose one signal, if you convert one signal to another, convolution, there are many things. Unique shift with the signal. So how you do that? We're going to learn how to operate with the signal. And that's what just to explain that x of n here, that's the sequence now. It means you substitute by every t and ts, and that's integer. Of course, you say you have negative here. Yes, the signal I explained the sign start from zero, but there is no problem. It will be start from the negative side. So at this time we have negative integer like -2, -1, -3, and so on. So you can have negative or positive, but n should be integer, no fraction. And that's an example. You have a signal, x of t, and we need to plot the continuous times. That's the continuous times, because it's defined. I'd like you try, every two students, just try to solve the first part. We'll go one by one. Give you like 2 minutes. We can discuss it together. I'm not going just to wait. No. When you get some solution with the friend, just tell me, okay, we got the sketch to see how you do it. So the first thing we want to learn how to sketch a continuous time signal given in this one. I know you had it in math before, but I want to make sure that you know how to do it. So x of t is equal to t from -2 to 0 and 0 and 2 going from 0 to 2 and then 0 otherwise. So it's like you can say you're going to sketch between -2 and 2 and the rest will be 0. Go ahead and try to sketch. So this one is just like straight line, and that's a constant. Okay, anybody did it? All right. Yes, that's fine. So it's done here. Let me sketch this. Somebody got to try it. So when you do, that's x-axis, and it said from -2. So you have -2, -1, 0, 1, 2, and the rest 0. And that will be the y-axis. And you have here 1, 2, -1, -2. The first part, t, xt is equal to t from -2 to 0. That's from -2 to 0. The x will be equal to t. So if you make a small table or short table, it's t, that's x. When t equal, it's straight line. When t equals 0, x equals 0. When t equals -2, x equals -2. It's a straight line. So you have here, that's 1 point on the straight line, and that's 1 point when x when t equal -2, the value of x of t is equal -2. So that's straight line. And it's 2 from 0 to 2. All right, from 0 to 2 is equal to, will be like straight line like that. And the rest is 0. Zero, 0. So that would be the same. That was the first part. You should be able to sketch any simple signal like that. So that's the continuous time signal. Now we want to sample the signal by sampling interval equal to 1 second. It means every 1 second you want to slice it. So try to sketch the sample one. And I will put here the graph so you will know how to do it. And I'll write the function here, x of t is equal to t when t greater than 2 than 0, 2. So that's the function. I need you sketch xn. Xn, you have to make the same graph, but you will not have time. You have the integer n. So you have here 0, 1, 2, 3, 4, and so on. And you have here -1, -2, -3, -4, and so on. That's the x-axis will be n, the integer n. So the continuous time signal, you sketch the function x of t against t, against time t. But discrete time signal, you sketch the sequence x of n against n, integer, the index n. Okay. So try. You got it? You're still. You got it. So if you have sampling every t, it means you will have at -2. You got to know that the sampling time is equal 1 second. That's easy. So you know t is equal n time ts. From that, you can find n. So n is equal t over ts, right? So when you choose -2, the time, and ts is equal 1, so the result will be -2. So n is equal to 2. What is the value when n equal -2? The value you have it here, -2. So that's -1, that's -2. This is at n equal -2. Then you go when at t equal -1, that will be corresponding to n equal -1, because ts is equal 1, just easy. If ts is different value, you will find different value. So you will find the value is equal -1. So you have -1. At 0, it will be 0. When you go at 0, at 0, but had 2 values. So you have another value here, 2. So choose the one, 2. That's 1, that's 2. And 1, it's 2. At 2 is 2. So you have 1, 2, 3, 4, 5. And the rest will be 0. Like at 3, there is nothing there. Will be 0, 0. You can make dots like that. 0, 0, the right and the left. You will be in the practice exercise that you'll solve to give it to you like different than TS equal 1. TS1 is equal 1. Think about what about if TS is equal 0.5? What you're going to do? Yes.
So the TS, the sampling time, just increments up with the time as well, right?
Exactly.
Okay.
Yeah, it's like increasing every 0.5.
Okay.
Like if you take TS 0.5
Okay.
and you start to slice. So what you'll have now at -2, that's the first one, right? At -2, you're going to have 1 sample. And then you move 0.5. So you reach -1.5, right? So let me do it in the same graph here that we have. And now I'm going to slice it every 0.5. And just let's make it red here. So you have 1 here, so I put dot here. And I move -5, so I reach this point -1.5 because I'm moving every 0.5. So I will go there, and then I'll have value here. And then move another 0.5, I get this point. 0.5, I will get one, another one. And then here I will have another one. So I'm moving every 0.5 seconds. Of course, you are going to have more samples, right? And the rest will be 0. And also the 0, you be careful. It should be every 0.5. So that's what I got. So that's what you get if you remove the, that's the samples I want to get. And then if you want to mark n, of course at 0, n is equal 0. So that's n equals 0. And this one, n is equal what? -1, right? -2, and so on. So the sample itself, it depends on the period, and the number of samples will increase when the sample time is small. And of course, that would be better because you can get the same shape, almost the same shape when you have. That's why when you have in the computer many bits, you get better picture, better text, everything, because you get all details. You're not missing a lot. Of course, you make sampling a lot if it's changing. But for this one that was constant, you don't have to have many samples because it's constant. But thing is changing with time a lot. You got to make more sampling. Okay. But we are focusing in this course when you make sample, you just to make it uniform sampling. They are equal. You don't have to change from 1 to 1. So that's how we make the sampling to convert from continuous to discrete. Yes.
Are we ever going to have to worry about sampling time that is different?
No. It's not in the course scope. Yeah, no. So I have here problems for you, for people online to do it, and we'll continue. Now we'll go for another classification. Does the signal repeat itself or not? What does it mean? Some signal repeat itself every certain amount of time, like sinusoidal wave, for example. We call this periodic if it's repeated every period of time. Like if you have a waveform and it's finished after 3 seconds, and then another 3 seconds, it repeats the same shape every 3 seconds. So we say that this signal is periodic signal of period equal 3 seconds. But the other signals that they do not repeat, we call it aperiodic or not periodic. Aperiodic or not periodic. Now we are looking for periodic signal. Periodic signal in both continuous time signal and discrete time signal. When you look at this table, that's the condition to be period signal. X of t is equal x of t plus t capital, which is the period. What does it mean? It means if you have signal like that, I say it's a periodic signal F. If you draw any line at any time t, because this axis is the time axis. If you draw any line at time t, and you make another line, the distance between them, t capital, and you'll find the same value. They are equal, so it's periodic. You don't do it over only one time. No, every time you add t capital to the t, like, I mean, if you continue, and if you have another one here and you continue, you'll find you get the same value. It means periodic. So when x of t equal x of t small plus t capital, so this will be the period. Yes.
So like it would be like every 5t, if it's the same number.
Why choose 5?
I'm just gonna get rid of it.
Oh, okay. You don't say 5t. You say, for example, if you say x of t, let's say that you are assuming now the period is equal 5 seconds and a thing. So you say x of t is equal x of t plus 5, x t plus 10, x of t 15. That's what you mean?
Yeah, it repeats.
Yes, yes, you add 5 every time. So if period t is equal to 5, so you say x of t at any time t is equal to xt5, xt10, and repeating. But the minimum one here, 5, right? Because it's repeat also at xt plus 10, xt plus 15. The smallest one here, 5, we call it the fundamental period. Because 10 also is a period, but it's not the fundamental. It's the smallest time that it will be repeated, because it's repeat after 10 seconds also, right? So can you say that the fundamental period is equal to 10? No, it's not fundamental. The fundamental, the smallest period that will be repeated, the smallest thing after 5 seconds. And obviously, if you say that in this example t is equal 5, it means from here to here, from this point to this point is equal 5. From here is equal 5. It's repeating every 5. Take any time t, you add 5, it's repeated. So that's periodic. And you don't have to have integer, by the way, because you choose 5, I choose 3, but no, you can have period equal to 10.75. Can be this one. Why I'm saying that? Because in discrete time signal is different story. So you have here a signal. Check yourself if you understand. Is it periodic? Yeah. If so, what is the period? The value of the period. Fundamental period. 4 seconds. Let's see. If you start here at this time and then you go down, you go up, finish. Yes, that's right. 4 seconds. All right. That's easy for the continuous time signal. All right. Can you calculate the frequency? If I ask what's the frequency of the signal? 1/4. Right. Do you know what is the meaning of frequency? 0.25, right? What is the unit of the frequency? Hertz. What's hertz? Hertz is the name of person, right? But originally, what's hertz? Cycle per second. So it means when you say 0.25, it means every second they're going to say what? You're going to see 1/4 of this. That's 0.25. Let me change this example to make it. If I change the number, just let's take a shot here. let's say that I will change a little bit. If I increase just about 0, I'll put 0 only. All right. Now it's still periodic, right? What is the period here? T. 40, exactly. 40 seconds. Okay. What does it mean, period? Means the time that the signal will start and end over one period, right? It will, one period, it will take 40 seconds. Now, my question again, F. What's F? F over 1 over T, the frequency. And everybody knows it's 140. Okay, I'm sorry. I want to change and make it the time smaller, actually. Let me make it smaller. I'm sorry. I want to make it smaller. So I will say this is 4 over 1000, 2 over 1000, because usually the time is really small. I try to be close to the real signal, usually in millisecond, microsecond, the period. Okay, so if you have this, so I'll say that the period is equal 4 over 1000. 0.004 second. So one period take 4 milliseconds. That's right, 4 milliseconds. When you calculate the frequency, will be 1 over T, will be 1000 over 4. So you have 250 hertz. What does it mean 250 hertz? It means 250 cycle per second. It means in 1 second, you are going to see 250 cycles. Complete cycles of this thing. That's the meaning. There is another way to calculate the frequency. They call it the angular frequency, which is called omega. What's omega? 2 pi f. 2 pi times f, which is 250. That will be 500 pi, and you can get the whole number, and it's in radian per second. Why they're doing that? Because it's frequency, it means you finish one cycle, right? Usually one cycle, when you look at the circle, it starts from 0 and finish one cycle, you reach 2 pi. So I said, okay, I want to find the equivalent. So that's why we use angular frequency. Consider every cycle 2 pi, 2 pi, and that's it. And used a lot, of course. Yeah. So that's the omega, the angular frequency. They call it angular frequency. All right, so we're done with the continuous time signal at the period. Let's go to the discrete, because it's a new concept. They say that in discrete time signal, it's periodic if x of n sequence at n, like 1, 2, 3, 4 in a number, is equal x of n small plus n capital. So we are going to say that this is periodic if it's repeated every number, certain number, like say n equal 10. So I say x of n is equal n plus 10, equal xn plus 20 plus 30. So it means that the period is equal 10 samples, right? But n has to be positive constant. The smallest n satisfied, like exactly the continuous time signal, we consider the fundamental period. And the same thing, f is equal 1 over n, and omega is equal to pi f, which was 2 pi, with f equal 1 over t over n, it's the same. But there is something about the discrete time signal. I will show you some rules that you're supposed to. Yeah, that's the example. You have signal, right? Discrete time signal. Can you tell me the period? Guess about it. Is it periodic? Yeah, obviously it's a period process. So the period is equal 5. All right, let's check. Yes, that's right, 5. So how do you know 5? I think you look at starting from here, right? And going, and then it will start again here, right? So you say 5.
We can't see your writing.
For me?
Did you just write on it on your screen?
Oh yeah. I have to take a shot again because I'm in. So you start here 0, and then you will start again. So when you count the samples, you start counting from 0. That's sample 1, 2, 3, 4, 5. Then it will start again here, right? It's good you count it from 0, but I'm just why I'm doing that, because maybe the signal will be given to you not starting from 0, from another number. Like imagine if for a while, if it was given just from here, start from here. So you got to think about it. This is here, and it will be start again back here at 6, right? So how count you don't say n is equal 6? It happened one time in the quiz. Said okay, n is equal 6. I didn't get the 0. So no, I mean when you start the beginning and the end, subtract will be 6 minus 1 be 5. So you have to be worried about that. 0, it's easy. You can get it. Okay. And you can check, of course. You pick any n and you add 5, you find it's the same value. That's how you find the frequency, 1/5. How you find omega. By the way, omega, write on capital omega to distinguish between the continuous time signal and discrete time signal. It's equal to 2π/5 because 2 by f, and f is equal 0.2 will equal 1/5. It's the same rule, the same rule. Now we'll go for the sinusoid. I want to make sure that I'm not exceeding time. Okay. Now we have the sinusoidal as special case of periodic signal, and it's very important. We're going to use a lot. So that's the sine wave. So how you find the period? Usually the equation given like that: x of t is equal to sine omega t plus theta. To find the period, look for the omega, all right, and the period equal 2π/omega. Simply because 2π is equal omega times t. The angle is equal to the frequency times the time. But this is again t is the period is equal to 2π radian over omega the number of years. For example, here I have example x of t equal to sine 3πt. So where is omega? 3π, right? So that's 3π. So omega is equal to 3π. How you find the period? 2π divided by omega. Then you got 2/3. It's okay to have fraction for the period in continuous time signal. I'm saying that again because now we're going to look for the discrete time signal. For discrete time signal, you got sinusoidal wave. And it's written cosine omega n, not t. And it's integral branches. Plus there, another number. How you find the period? You say 2π/omega. All right. But there are conditions. First of all, let's look at this one. It's given x of n sine omega n. So omega is equal π/12, right? So that's omega π/12. Don't care about that. How you find n, the period? You find 2π/omega. Exactly. Like 2π/omega. But this is capital, this is small. So 2π/omega, but we add something here, times n, and I'll tell you why. 2π/omega, 2π, and that's omega π/12, π/12, pi cancel pi, and you have 2 with 24n. Well, I'll tell you now why I'm adding n. Choose the smallest integer of n such that the value of n is an integer. Like n capital is equal to 24n. Choose the smallest value, which is 1. You can choose n as 1, 2, 3, 4. You try plug numbers, integers, till you get what? Till you get integer. If you didn't get integer, so it's not it doesn't have a period this time. So in this case, I put n equal 1. It's 24. So the period is equal to 24. The fundamental period is equal to 24. Okay. Let me. That's the fundamental. Let me take another example here. Look at this one. Oh, we have two examples. X of n equals sine omega n plus n. So we want to find the period of this one. How do you find the period of this one? Yes.
I just have a quick question.
Yes.
So to clarify, you said keep plugging in values for n into the integer.
Yes, integer. Yes. And the smallest integer, it will produce you the fundamental period. Yes. Now look for the first one. That's omega. If you just try so omega, right? 3 pi over 10, and you want to find n, the period. So we say 2 pi over omega, right? 2 pi over 3 pi over 10. What do you get? Somebody, can you tell me the answer? Okay. Here, the first one. I have omega is equal 3 pi over 10. So n capital will be equal 2 pi over omega times m. 2 pi over omega. Omega is equal 3 pi over 10, right? That's 3 pi over 10 times m. So what you get pi cancel pi. So you got 20 over 3m. Obviously, if you put m equal 1, what you'll get? 20 over 3 is not integer. So it cannot be period. You see what I mean? You put 2. If you put 2, you have 40 over 3. Still, it's not integer. You put 3,
60.
you got 20, right? So 20 over 3. The smallest integer you can plug here, it will give you integer number. That was 3. So the period is equal to 20. Because it should be integer. Why it should be integer? Simply because we agreed from the beginning, when you have discrete time signal, the x-axis, which is n, should be integer, right? 0, 1, 2, 3, 4, 5. So you cannot have 1.5, 1.6. No. That's why I multiply by m to try to figure out which is the smallest integer. Did you get this point? Right. Try the second one. The second one, omega equal 3, right? Yeah. So I say omega equal 3. So n is equal to 2 pi over omega times m. If you try your best, choose any number, you will never get an integer for simple reason. Because you have pi. Pi is irrational. You can't choose any integer. You can't. Any integer, you can't. So what's happening here? Doesn't happen? Exactly. Yes. I think I made the point. Yes.
So the value of m
has to be integer. Yes. Good question. Was not periodic. You can't find any integer to it. Can't. So you can't. And this is discrete time signal. You don't have any integer that it will. You can find it to be repeated. So it's not. Yeah, the first one is periodic, and the period is equal to 20. The second one is aperiodic. Yes.
So can you explain again what n equals to 3?
Why it's equal to 3?
Yeah.
Because when we try to plug other numbers, here you have 20 over 3 times m. Start with m equal 1. What's the result? 20 over 3. It's going to be fraction. Can you have n fraction? Because n capital is a period, but at the same time it will be an index. What do you mean index? Just let me remind what's index. Because we agree that t is equal n ts, right? And n we agree they are integer, like 0, plus or minus 1, plus or minus 2, and so on. So n has to be integer, and n capital is a period and number of samples. It should also be integer. So you have to find the smallest integer, and when you multiply by 20 over 3, you get integer. Because n is integer. Cannot be not integer. Yes. Pardon me? Oh, you mean this number? Of course, if it's given like that. Of course, if it's fraction, yes, it'll be the same. Fine.
And then that makes n the period equal to 1. Okay.
Yes,
That makes sense.
exactly.
Thank you.
You're welcome. There are some exercise when I post this file. You can go ahead and try it. I have the final answer. You can check. That's always when you study and you go through the notes, you'll find I have checkpoint. Means you got to stop, to move to other point to make sure that you got the previous point understood, or they are accumulated. Now that will be the last thing about the period. What about if you are adding two periodic signals? Two periodic signals you are adding. You should have a periodic signal, right? Not necessary. Because it depends a lot, you know, when you are adding a thing like that. So let's just, I will give you very simple rule without proof how you can get it. You have x1 and x2, both are periodic signals. And their periods are known, T1 and T2. And I added them. They said that if you want to know that the sum of both periodic signal is also periodic signal, divide that their periods like T1 over T2, T2 over T1, doesn't matter, just divide them. And if the result of the ratio T1 over T2 is equal integer over integer, it is. Let's say it by a numerical example. You have two functions, x1 of t equal cosine pi over 2. x2 is equal cosine pi over 3. So I can find the period of t1 and t1, right? You can, okay, go ahead and add these two. Find t1 here and t2 as exercise. You know how to find t2 pi over omega. And tell me what the result. Okay, did you get it? T1 will be equal to pi over omega 1. Omega 1 is equal pi over 2. So that be 4. T2 is equal to pi over omega. The second omega is pi over 3. Pi cancel by b6. So 1 is equal 4, the other is equal 6. So what you're supposed to do, you just divide T1 over T2. It will be equal 4 over 6. And then simplify. What you get 2 over 3. The result in the end, it's a fraction, but the top and the bottom, both are integer. So say, okay, the sum of x1 and x2, it's going to be periodic. The question is, what is the period of the resultant? What is the period of the new wave that results from the sum of both? Very simple. T called T of the sum will be equal if you just multiply this or this, both are the same, right? Because I mean, if you multiply 2 by T2, it's the same as 3 by T1, right? Anyone you get, this is the period of the new waveform. T2 is equal 6, right? That's 12. What's 3T1? What's T1? 4 is equal 12. So the period of the sum of both signals is 12. So it's easy to find the if it's periodic or not. Some cases, of course, you will find that you can't get the sum. The last thing is simple, doesn't have any math. Sometimes they call the signal deterministic, and sometimes they call it random. What is the difference between deterministic signal and random signal? Deterministic signal that you can express it mathematically, like I'm doing here. It's 2 times exponential from sine. You can go to the lab and get measured, and not only measure, and you can express it by equation, determined by equation. But random signal, by the way, that's continuous signal. The same thing for discrete signal. You can have expression. But random signal, it's something just, you cannot express it by mathematical equation, but usually use probability and statistic to express it. Because it's random, it's not constant, it doesn't have shape, the shape is changing, it doesn't have a formula. So we use probability to express. Usually used also like for noise. You will hear something called white noise, that it has some kind of shape and just probability, Gaussian, all the thing. But you cannot find mathematical expression like sine, exponential thing, you can't. So that's the difference between both. And sometimes the random, if the random signal, they can approximate it, they can, but they cannot find exact equation that can represent that. That's why they call it random signal. They are, but they are alive. They exist. I'm giving you an example for electromyogram EMG that they used in bioengineering and medicine. They saw the activity in skeletal muscle that's used for diagnosis for some disorder in the nerve. That's one of the examples of random signal. You cannot express by equation. Can you express by equation? It's not sine, not equation like that. But just they take the data and the measurement and they compare it and they deal with that. They deal with that using statistics and probability. I'm going to stop here because next time I'm going to continue will be just one left, even and odd, and it's easy, but next time. Do you have any question? Yes.
These slides, will they be posted on the folio?
Yeah, usually I post after the lecture. Yes. Don't. Yeah. And even the video, I will upload it. Yes.
So the slides you always post them after the lecture.
After the lecture, yes. If you want me to post before, I can.
Okay.
You like?
Yeah.
All right. I'll do. Yes.
Do you record these lectures? Am I uploading them? Do you record these lectures?
Oh yes, I do.